This is lecture 1D, and we've been working on calculating equilibrium data from non-equilibrium data and then some other type of clue given in the problem somewhere. We've already done a few examples like that. Essentially, these are kind of like murder mysteries. If you ever used to watch Columbo, the detective from Los Angeles who would solve mysteries, he would track down the clues and figure out who committed the murder or the crime. Or if that's too old for you, maybe you've seen CSI. They're always looking for clues to try to figure out the answer to the mystery. Or if maybe police shows are too violent for you and you don't like that, then maybe Murder, She Baked, where a baker actually solves murder mysteries by searching for clues. But whichever is your cup of tea, every type of equilibrium calculation where you're trying to determine equilibrium data from non-equilibrium data will quite often involve some type of clue that you have to deduce from the problem. We're going to look at some examples of that today. If we take the decomposition reaction of ammonia, where ammonia turns into nitrogen and hydrogen, let's say 2.0 moles of ammonia are placed in a 1.0 liter container. At equilibrium, 1.0 moles of ammonia remain. Find Kc for the above reaction. So we're given non-equilibrium data right at the beginning. 2 moles of NH3 are placed in a 1 liter container. We want to calculate an equilibrium constant, which is based upon the equilibrium molarities of the products to the reactants. So we're looking for equilibrium data. Anytime you're looking for equilibrium data, but you're given non-equilibrium data, then we're going to do an ICE table for that. And to do an ICE table, we've got to do it in terms of the Kc, which is ratios of molarities. They didn't give us the molarity of the ammonia, but we'll have to calculate it. It's just the 2.0 moles divided by the 1.0 liter. And so the molarity of the ammonia is actually 2.0. Now, they did give us one other bit of information in the problem. They said at equilibrium, 1.0 moles of ammonia remain in the container. So we can calculate the equilibrium molarity of the ammonia by taking the moles that are in the container at equilibrium, dividing by the volume. That comes out 1.0 molar. So now that we have the data in the proper units, we can set up an ICE table in terms of initial, change, and final molarities. Here's our equilibrium reaction. The initial molarity in the container was 2.0 for the ammonia, and nothing else was in the container, so the nitrogen and the hydrogen are both zeros. Because there are no products, the spontaneous reaction has to be the forward reaction. So the ammonia is going to react away, and 2x of it's going to react away. We're going to form 1x of nitrogen, 3x of hydrogen, and adding the columns will now have the equilibrium molarities of the ammonia will be 2.0 minus 2x, the nitrogen will be x, and the hydrogen will be 3x. Once we've determined our algebraic equilibrium molarities, we're now going to relate those to equilibrium constant. The equilibrium constant equals the molarity of the products divided by the molarity of the reactants. That would be the concentration of nitrogen of the first, multiplied by the concentration of hydrogen of the third, divided by the concentration of ammonia squared. The Kc we don't know, but we do know all the equilibrium molarities of the reactants and products, and so if we plug them into the expression, we're going to get something that looks like this. Now, the problem here is we have two variables, and this is where as soon as you have an algebraic expression with two variables, you need to search out a clue somewhere in the problem that's going to let you calculate the first variable so you can find the second. We need a clue to calculate x so that we can answer the question and calculate what the Kc is. And the value for x is going to come from this extra bit of information that was given in the second sentence. The equilibrium molarity of ammonia is 1.0. So what's the equilibrium molarity of ammonia? Well, look under the ammonia in the equilibrium line. It says 2.0 minus 2x. So 2.0 minus 2x has to equal the 1.0 molar. This is going to allow us to figure out what x is. And so if I do that here on the next page, the equilibrium molarity of ammonia, which we've determined is going to be 1, it was given in the problem, has to equal our algebraic expression of 2.0 molar minus 2x. So if I want to solve this for x, I'm going to subtract 2.0 molar from both sides. That's going to give me negative 1.0 molar equals negative 2x. Divide both sides by negative 2, and I get x equal to 0.50 molar. The negative 1.0 was a 2 significant figure number, but the 2 that I divided by, the negative 2, that's a counted number. So with only the 1.0 being a measured value, 2 significant figures, my value for X comes out to be 2 significant figures. So if we go back to the Kc expression we had written before, and remember we had plugged in all these equilibrium molarity values based upon our ICE table, we now know the value for X. So in place of all of those X's, I'm going to put 0.50 molar. If I do that, then the molarity of the nitrogen is going to be 0.50 molar. The molarity of the hydrogen is going to be 3 times 0.50 or 1.5. And the molarity of the ammonia is going to be 1.0. The answer is going to be 2 significant figures. And if I calculate what the units should be, I have molarity to the 4th on the top, molarity squared on the bottom. That divides out to be molarity squared. My final answer, 1.7 molar squared. Let's take this equilibrium reaction. SF4 is in equilibrium with SF2 and F2. A container has an initial SF4 concentration of 0.308 molar. When the container reaches equilibrium, the SF4 is found to be 35.0% dissociated. Calculate Kc. So another problem where we've been given initial information, non-equilibrium information, 0.308 molar of SF4 is initially put into a container. We want to know something about the equilibrium condition, its equilibrium constant. So we're going to need to know all the equilibrium molarities of the reactants and products to calculate that Kc. So we're going to have to do an ICE table to get those equilibrium molarities of all the reactants and products. So if we take our equilibrium reaction and complete an ICE table for that, and because we're calculating a Kc, the ICE table will be initial molarity, change in molarity, equilibrium molarity. The initial molarity of the SF4 was 0.308, and that's all it said was placed into the container, so we can assume there are no products. Because there are no products, the spontaneous reaction has to be in the forward direction. We'll react away 1x of SF4, we'll produce 1x of SF2, and we'll produce 1x of F2. Adding the columns, the equilibrium molarities are going to be 0.308 minus x, and x. Once we've completed an ICE table, you want to write the equilibrium constant expression that relates the equilibrium constant Kc to these 3 equilibrium molarities that we've just determined algebraically. So the Kc is the concentration of SF2 multiplied by the concentration of F2 divided by the concentration of SF4. We know the equilibrium values for the 3 reactant and products. And then once again, we have a situation where we actually have 2 variables. We're trying to get Kc, but we also have this variable x. So there has to be something in the problem that's going to allow us to calculate the x first so that we can then determine what the Kc is. And the only other bit of information given in the problem was it says at equilibrium, the SF4 is found to be 35.0% dissociated. So if we think back to what that means the percent dissociation is the amount of the SF4 that dissociates or reacts away divided by the original amount placed in the container multiplied by 100. So where's the amount of SF4 that reacts away? It's under the change line, directly under the SF4. What does it say there? X. So X amount will react away out of the 0.308. If we take that fraction and multiply it by 100, that will equal the percent dissociation, which is 35.0%. So our definition of percent dissociation says the 35.0% equals the amount that dissociates, which is X, divided by 0.308, multiplied by 100. You can solve that expression for X, and if you do, X comes out to 3 significant figures, 0.107, with a guard digit of 8. So now that we know the value for X, we can now plug that value in place of X into our Kc expression. Here was our Kc expression. Here it was with the equilibrium values from the ICE table. And now that we know the value for X, we can plug in 0.1078 in each of the spots for X. The units are molarity squared on the top, molarity on the bottom. So the final units will come out molarity. And because the numerator and denominator will both be 3 significant figures, the answer will come out 3 significant figures once we've done it. And that turns out to be 0.0. And then we start counting our significant figures, 580 molar. And that would be the equilibrium constant for this particular reaction. Let's try this reaction. NH4Cl solid is in equilibrium with NH3 gas plus HCl gas. 1.00 grams of NH4Cl is placed in a flask, and the total pressure at equilibrium is 0.600 atmospheres. Find Kp for the above reaction. So as before, we're given some initial data. 1 gram of the ammonium chloride is placed into a container, initial conditions. We're trying to find something about equilibrium. What's the equilibrium constant? We'll need to know all the equilibrium pressures in order to get the Kp for the reaction. So if we take our reaction and we do an ICE table, and because we're trying to find a Kp, the ICE table is going to be for pressures, so initial atmospheres, change in atmospheres, equilibrium atmospheres. So the first question is, well, what do we put under the NH4Cl? It says 1.00 grams of NH4Cl. How do we switch that into atmospheres? And the answer is you don't, because NH4Cl is a solid. Solids do not exert a pressure, and in fact, solids don't even appear in equilibrium constant expressions. So anytime you're creating an ICE table and you have either a solid or a liquid as a reactant or product, there's nothing you write underneath that because it does not have a variable concentration or a variable pressure, so we can't actually place anything there. The only thing we're going to write are the things under the two gases. So we actually put NH4Cl in the container, but we didn't put anything else, so that means the container, in terms of its gases, had no ammonia, no HCl. The solid NH4Cl, though, because that's the only thing in the container, will actually start to decompose. So as some unknown amount of it reacts, which we'll call X, we will form 1X of ammonia and 1X of HCl, still based upon the coefficients in the balanced equation, no different there. And the equilibrium pressures will be X and X. So now you've seen if you have a solid or liquid in your equilibrium, you don't write any data under that because it will not have variable molarities or variable pressures. Once the ICE table is complete, we write the equilibrium constant expression. It's a Kp expression, so it's going to be the partial pressure of NH3 multiplied by the partial pressure of HCl, and that's it, no denominator. We know the values of the two pressures, they're X and X, so therefore Kp is going to equal X squared. And for the third time in a row, we now have a problem with two variables. We've got to figure out X before we can figure out the Kp. The extra bit of information, the clue given to you in the problem, is that the total pressure at equilibrium in the container is 0.600 atmospheres. So what does total pressure mean? That means the sum of the pressures of all the gases in the container. So how many gases are in this container? There are two of them, NH3 and HCl. So the total pressure is going to be the sum of the partial pressures of the NH3 and the HCl. Now, what were their partial pressures? At equilibrium, they're both X. So therefore, the total pressure of 0.600 atmospheres must equal X plus X. 2X equals 0.600, X equals 0.300. And now that we've calculated what X is based upon total pressure, we can use that X value in our Kp expression, and we can determine that the Kp for this reaction should be 0.0, and then three significant figures, 900 atmospheres. If that makes sense, we can give you one of these types of problems to see if you want to try to work out on your own. 2N2O gas is in equilibrium with 2N2 gas plus O2 gas. A flask is charged with 0.450 atmospheres of N2O, and when equilibrium is reached, the total pressure in the container is 0.500 atmospheres. Find Kp for the above reaction. If you want to take a moment and pause this and try to do the problem, go ahead and do it, and then we'll go through the answer. So we're going to write an ICE table for this reaction. The ICE table is going to be initial pressures, change in pressures, equilibrium pressures, because we're trying to find the Kp. They've told us the initial pressure of the N2O, it was 0.450. That's all they put in the container, so there's no nitrogen, no oxygen. The spontaneous reaction has to be to the right, so 2X of the N2O pressure is going to react away. You're going to form 2X of the N2 pressure and 1X of the O2 pressure. Adding up the columns, you'll have the equilibrium pressures of all three substances, 0.450 minus 2X, 2X, and then X. The equilibrium constant expression for this reaction, partial pressures of products over partial pressures of reactants, will be the partial pressure of N2 squared multiplied by the partial pressure of O2 divided by the partial pressure of N2O squared. We know the equilibrium partial pressures of the three different gases, so the Kp is going to equal 2x quantity squared times x over 0.450 minus 2x quantity squared. And if we're trying to get the Kp, we have this other variable in the problem, the x, which we're going to have to figure out first. So there's got to be a clue in the problem that's going to allow you to determine x, and the other bit of information given in the problem is total pressure. So once again, what does total pressure mean? It means the sum of all the pressures of all the gases in the container. How many gases are in this container when it reaches equilibrium? The answer is 3. There's N2O and N2 and O2. They're all going to be there. So the total pressure is going to be the sum of the partial pressures of the N2O, the N2, and the O2. The total pressure is 0.500 atmospheres, and we know the partial pressures for each of the gases. The N2O is 0.450 minus 2x, the N2 is 2x, and the O2 is x. The minus 2x and the positive 2x cancel out, and that leaves 0.500 atmospheres equals 0.450 plus that final x. Subtracting 0.450 from both sides, x equals 0.050 atmospheres. And now if we know the value for x, we can plug that back into the Kp expression, and we can calculate our equilibrium constant. So here's the equilibrium constant once again, and here it is with all the x values in it. If I plug in the 0.050 in place of all of the x's, I will be able to calculate the pressure of the nitrogen, the pressure of the oxygen, the pressure of the N2O, and if I square them appropriately, I'm going to get my Kp value. I have atmospheres cubed on the top, atmospheres squared on the bottom. The answer is going to come out atmospheres, and to two significant figures because of the 0.10 and the 0.050. The answer comes out 4.1 times 10 to the minus third atmospheres. Now our final concept in our chapter on equilibrium has to do with a principle derived by Henry Louis LeChâtelier back in 1884. This is called LeChâtelier's principle. And in most high school chemistry textbooks, you may have seen it before. It's almost always written like this. If a stress is applied to a system at equilibrium, the equilibrium will shift to relieve the stress. I have no idea what that is. Sometimes I'm under stress and I don't know how to relieve it. And so how do you apply this to a chemical reaction? I find this very disconcerting. So I have a slightly different definition for LeChâtelier's principle. Here's how I like to think about it. If a system at equilibrium undergoes a change in either the concentration of a substance, temperature, volume, or pressure so that it is no longer at equilibrium, then either the forward or reverse reaction will become spontaneous until the system reaches equilibrium again. I think that makes a whole lot more sense, and what we want to be able to do is use this LeChâtelier's principle to predict if a system is at equilibrium and then you change something, you change the concentration of a reactant or product, you change the temperature, change the volume, change the pressure, it's going to cause the system to go out of equilibrium. Which reaction is going to predominate until the system goes back to equilibrium? Will the forward reaction predominate over the reverse, or will the reverse reaction predominate over the forward? And that's sort of the question we're going to try to answer. So we're going to use a couple of different reactions as examples to illustrate LeChâtelier's principle. We're going to use this reaction between hydrogen and iodine gases to produce hydrogen iodide. And I'm going to do a bunch of different things that will cause the system to go out of equilibrium. And the first thing we're going to do is we're going to say hydrogen gas will be added to a container that was theoretically already at equilibrium. So if the system's at equilibrium and you add hydrogen, we want to answer the question, which reactions can become more spontaneous, the forward or reverse? And the way that's usually phrased in terms of LeChâtelier's principle is which way does the reaction shift? If the forward reaction becomes more spontaneous, we say it shifts to the right. If the reverse reaction becomes more spontaneous, we say it shifts to the left. Then I'll ask you, okay, once it reaches equilibrium again, what's going to be true about the moles of the HI at our new equilibrium? And then what's going to be true about the concentration of the HI at our new equilibrium? And to figure out the answer for this, I'm going to do a quantitative example. I'm going to make up numbers for this particular reaction. I'm going to assume a reaction's at equilibrium, and I'm just going to make up the molarity of all the reactants and products. Let's say I have 10 molar of hydrogen, 10 molar of iodine, and 40 molar of HI, and at whatever temperature, these are the equilibrium amounts of all three substances. If they're the equilibrium amounts, I can calculate an equilibrium constant, products over reactants. That would be 40 squared divided by 10 times 10. So the equilibrium constant in my made-up example comes out to be 16. So what we want to do is we want to go, well, what's going to happen if I add hydrogen to that? So if I add hydrogen, that means my molarity of hydrogen is going to be higher than 10. So I'm going to put in a number bigger than 10. You can pick whatever number you want as long as it's bigger than 10. How about 28? So if I add just hydrogen in the container, the hydrogen concentration's higher, but the iodine and the HIs aren't. So what does this cause to happen? It's probably not at equilibrium anymore, because probably 40 times 40 over 28 times 10 doesn't equal the equilibrium constant of 16 anymore. If this system is not at equilibrium, we can calculate its Q value. Its Q value will be 40 squared divided by 28 times 10, and that equals 5.7. And so we've learned how to analyze this before. If the Q value is smaller than the equilibrium constant, then Q is going to eventually get bigger until it equals the equilibrium constant. If Q has to get bigger, that means the numerator has to get bigger. That's where the products are. That means the forward reaction must be spontaneous. So we can predict that we would say the reaction shifts to the right, because that's another way to say the forward reaction is now going to become spontaneous for a few moments until the reaction reaches equilibrium again. So let's see if we can quantitatively predict what would have to happen. If the forward reaction is going to be spontaneous, we're going to react away our reactants. So the amount of hydrogen is going to go down. Maybe it's going to go down by 4 moles per liter. And then the iodine would have to go down by the same amount because it's a 1-to-1 ratio. And then the HI would go up by twice that amount. So it would go up by 8 to 48. So once this change has occurred, our ratio is now 48 squared over 24 times 6. It equals 16 again. The system's gone back to equilibrium. So when we add hydrogen to the container, we cause the reaction to shift to the right, and it'll continue to be spontaneously reacting to the right until you reach the numerical values of 24, 6, and 48, when the system will once again be at equilibrium and both the forward and reverse reaction rates are equal. So if you look at these new equilibrium values, what's true about the amount of HI? There's more HI that's been created because the reaction's been spontaneous to the right. So this is going to have increased, and you can see the molarity of the HI is increased also. So therefore, by adding hydrogen, the reaction shifts to the right, and you increase the amount of the product HI, both in terms of moles and in terms of molarity. Another way to look at this, and it always works this way, is that if you increase a reactant, you're going to cause the reactant molecules to bump into each other more quickly than they were before. You're going to make the forward reaction go faster. So anytime you add a reactant, you've got to get rid of that excess reactant because it's going to react faster. So the reaction proceeds to get rid of that reactant, which means it has to shift to the right, or the forward reaction has to be spontaneous. If iodine were added, that's a reactant. If you add a reactant, you're going to cause more collisions between the added I2s and the H2s. You're going to make the forward reaction start going faster. You've got to get rid of that excess I2 you've added. So the spontaneous reaction will be the forward reaction. It's going to shift to the right. If it shifts to the right, you're going to produce more product. So therefore, the moles of HI will be greater, and the molarity of the HI will be greater as well. Let's try this. Let's say we add HI to the container. So what's going to happen if we add some additional HI? Let's go back to our made-up example where we have an equilibrium condition of 10 molar, 10 molar, 40 molar, and the equilibrium constant, as you may recall, worked out to be 16. So if I'm going to add some HI to this, I'm going to want to make my HI molarity higher than 40. So let's pick a number, maybe 52. So if I add more HI, that number will be larger, but the amounts of hydrogen iodine will actually be the same. So what's going to happen here is if you increase the amount of a product, you're going to make the product molecules collide with each other more often. They're going to cause a faster reaction for the products turning back into reactants. You're going to have the reverse reaction occur spontaneously. So we say the reaction shifts to the left. Conceptually, if you just increase the amount of HI, Once a system was at equilibrium and you add HI to it, you've got to get rid of that excess HI, so it's going to react away. And the way you react away the HI is by having the reaction shift to the left, or in other words, having the reverse reaction be more spontaneous. So when you reach equilibrium, some of the HI must have reacted away. Let's say 4 of them react away. If 4 HIs react away, you must be producing 2 I2s and 2 extra H2s. So now if we calculate the ratio of 48 squared over 12 squared, that equals the equilibrium constant again of 16. So we've reached equilibrium. So I want you to watch what's true for the answers for the last 2 questions here. HI was the substance we added to the container. It went from 40 up to 52. Whatever you add, you're going to react some of it away. But if it's the substance you've added, so now it has an abnormally high amount of its substance present, in this case 52, some of it will react away, but it's not all going to react away. The 52 goes down to 48, and then equilibrium is established. So although we are reacting away some of the HI, the equilibrium molarity of HI compared to its very original molarity is going to be higher. 48 is higher than the 40, and so the moles and the molarity will both be higher than each other. Let's try this. Let's say H2 is removed from the container. If you remove a substance from a container, that means that there's going to be less H2s in the container to bump into the I2s. If they don't bump into each other as quickly, the forward reaction slows down. So what reaction is dominating now? It's the reverse reaction. If we look at how that would work, if we have an equilibrium condition one more time with the equilibrium constant of 16, and I remove some H2 from the container, I'm going to make this a smaller number, so only 8 H2s. So if I've reduced some of those, the H2s and I2s will not be colliding with each other as often, so the reverse reaction is going to wind up having to be faster because the forward reaction is slowed down. You can show that mathematically by calculating a Q value for this new expression. It's 40 squared over 6 times 10, that equals 27. So by removing the H2, you've removed some of the hydrogen, you've caused Q to be greater than the equilibrium constant. To go back to equilibrium, Q has to shrink from 27 to 16. If it's going to shrink, you've got to make the denominator bigger, you've got to form more reactants, and forming more reactants means the reaction is shifting to the left, the reverse reaction is spontaneous. So to get back to equilibrium, you will lose a couple of HIs as they react away, and you'll form an iodine, you'll form a hydrogen, and now this new ratio of 38 squared over 9 times 11 equals the equilibrium constant of 16 again. Now, what's true about the moles of HI compared to how they were originally? Well, they're going to be less because the reaction was spontaneous to the left. You react away some of the HI, its molarity will be lower as well. So a general statement that's true is if you ever remove a reactant, that's causing a hole on the left side of the equation. The equilibrium is going to have to shift to fill that hole, and that would mean the reverse reaction. If you were to take away some of the product, there would be a hole on the product side. You have to fill that hole. The reaction would have to shift to the right, or the forward reaction would be spontaneous to reach equilibrium again. Let's look at this. What if we add helium to the container? How will that affect my 3 equilibrium molarities that I have below in green, 10, 10, and 40? And the answer is helium doesn't affect any of those. They aren't in the equilibrium. There is no helium in this reaction. So if you add an inert material, something that's not in your equation and does not react with any of the reactants or products in your equation, then it'll actually have no effect. The helium atoms will be occupying some of the space between the hydrogens and the iodines and the hydrogen iodides, but they won't affect their molarities, and so they will not cause the forward or reverse reaction to change their speeds. So this would have no change in the shift direction. You'd have the same number of moles of HI, and you would have the same number of moles or molarity of HI as well. So these are all effects of changing the concentration of something inside of a reaction vessel that's equilibrium. If you have a temperature change, you have to know something else about the reaction to predict how that's going to affect the reaction. You have to know whether the reaction absorbs energy or releases energy. And we have a couple of terms describing those. Endothermic is the term we use to describe any process that absorbs energy. And if you have a process that releases energy, we call that exothermic. And if you know a reaction is exothermic or endothermic, then when you write your balanced equilibrium equation, you can actually write energy as either a reactant or product in the equation, because that's going to help you determine how a change in temperature is going to affect the equilibrium. So energy can be treated as a reactant if it's an endothermic reaction because it absorbs energy, so it's acting as a reactant, or as a product for exothermic reactions because exothermic means energy is being released, so it would be a product. And if we write that down, we can use that to predict the shifts in equilibrium. And let's look at an example with a generic reaction, the gas AB breaking down into two smaller gases, A and B. And if we're told that this is an endothermic reaction, that means it absorbs energy. I can write directly on the reactant side plus energy. So the energy must be absorbed by the AB, this kind of makes sense, to break the AB apart into A and B. Now, what's a change in temperature going to do? Let's make up some numbers about a system that's at equilibrium. Let's say at equilibrium, we have 80 molar of AB, and we have 20 molar of A, 20 molar of B. The equilibrium constant expression would be the gas A times the gas B divided by the gas AB. And if we put their molarities in there, 20 times 20 over 80, the equilibrium constant comes out to be 5. If you were to raise the temperature, raising the temperature means you're adding energy to the system. Energy's on the left side. If you increase something on the left side, which way does it make things shift? You got to get rid of that excess material. It's got to shift away. So by raising the temperature, you're adding energy. Energy's on the left side. You've got to get rid of that. The reaction's going to shift to the right. We would say the forward reaction would become more spontaneous. Now, because energy is not matter, the only things that changes are these 80, 20, and 20. The AB will react away because the reaction shifting to the right, you'll have a lesser amount, and you'll wind up having a greater amount of A and B, and then you reach equilibrium. Now at this new higher temperature, the equilibrium constant is going to be 30 times 30 over 70, and it multiplies out to make 13. Really important point about systems at equilibrium. This is the only thing that can change the numerical value of an equilibrium constant. Equilibrium constants are constant as long as a temperature doesn't change. But if you change the temperature, you actually will cause, according to LeChâtelier's principle, the ratio of the products to reactants to be different, and you'll get a new equilibrium constant. This is the only type of thing that will change the numerical value of an equilibrium constant. Only changes in temperature can change the numerical value of an equilibrium constant. And in this case, when we for this endothermic reaction, when we raised the temperature, what happened to our equilibrium constant? It went up. If I would have done the opposite, if I would have decreased the temperature, I would be taking energy out. There would be a hole on the left side of the equation where energy is. You would have to shift to the left to create more energy. If you shift to the left, you're creating more AB, which is in the denominator. You're making a bigger denominator. You're making the equilibrium constant smaller. So if I would do another example where the temperature was decreasing, we would find that the equilibrium constant would wind up being smaller. Let's look at this equilibrium reaction. H2 plus I2 is in equilibrium with 2HI. Experimentally, we can use devices called calorimeters to determine how much heat is absorbed or gained in chemical reactions. And mathematically, that numerical value that's calculated is called the reaction's change in enthalpy, which is abbreviated delta H. This is the energy change during a chemical reaction. It can be experimentally calculated with calorimeters. There's thermodynamic data tables that can allow us to calculate it theoretically. But an important point about enthalpy changes is if the enthalpy change is positive, that means that the reaction absorbed energy, so it's therefore endothermic. If the enthalpy change for a reaction is negative, that means energy is released and the reaction is exothermic. So if you're given a reaction like the one at the top of the slide here, and you're told experimentally that the enthalpy change for this reaction is negative 5.1 kilojoules per mole of HI, the only thing that's really important here is the net sign of the value for delta H. It's negative. If it's negative, that means the reaction is exothermic. So you can take your balanced equation at the top of the slide and put energy as a product because energy would be released if the reaction is exothermic. Let's see if we can answer some questions about this reaction now. What if we increase the temperature? Well, you're increasing energy. Energy's on the product side. You've got to get rid of that excess energy. So which way does it shift? It shifts to the left. So the reverse reaction becomes spontaneous because you've got to get rid of that excess energy. What's happening to the amount of HI if the reaction is shifting to the left? You're decreasing it. The concentration of HI is also going down as you're doing that as well. So for exothermic reactions now, if you increase the temperature, because you're decreasing the products and you're increasing the reactants, you're making that fraction a smaller number. So here at equilibrium, the value was 80 squared over 20 squared equals 16. This would be the equilibrium constant for this particular reaction. And at a temperature where the temperature's been increased, you decrease the amount of HI, so that drops maybe from 80 down to 70. The H2s and I2s increase from 20 up to 25. The equilibrium constant becomes 7.8. It's become a smaller number. So as the temperature goes up, the equilibrium constant goes down. That's always true for exothermic reactions. An increase in temperature causes the equilibrium constant to go down. If you decrease the temperature, that means you're removing energy from the system. That's creating a hole on the right side. So the reaction has to shift to the right to fill that hole. So we would say the forward reaction becomes spontaneous. If it's shifting to the right, it's creating more HI. And so the concentration of HI will be larger. That's in the numerator. So you're going to have a bigger equilibrium constant. So for exothermic reactions, when you decrease the temperature, you actually increase the equilibrium constant. So that's how you handle temperature effects on systems at equilibrium. If you change the temperature, LeChâtelier's principle can predict whether the forward or reverse reaction would become spontaneous until the system reaches equilibrium again. I want to talk about volume changes as the final concept here. If we have a gaseous reaction, the gas AB decomposing to gases A and B, and the equilibrium constant we had calculated earlier for this one was 5. Let's say we start with a system at equilibrium where there's 80 molar of AB, 20 molar of A, 20 molar of B. If I have a 1 liter container, then that means there would be 80 moles of AB in that 1 liter container. That's how I get a molarity of 80 moles per liter. 20 moles of A, 20 moles of B. If I change the volume of the container from 1 liter to 0.5 liters, that's going to change all of the molarities. For the AB, instead of 80 moles per 1 liter, it's now 80 moles for 0.5 liters. And 80 divided by 0.5 is 160. 20 moles of A per 1 liter gets changed to 20 moles of A per 0.5 liters. That's now going to be 40 molar. And the same thing for B. If you ever decrease a volume, what you're doing is you're pushing the gas molecules closer together. You're making them more compact. You're raising their concentration. So making a volume of a container smaller raises the concentration of every single gas in the container. They're all different numbers than they were before, so it's probably not at equilibrium anymore. Let's figure out which way it's going to have to shift to get back to equilibrium by calculating a Q value. So with my volume decreased to 0.5 liters, my Q value is 40 times 40 over 160, which equals 10. And that's bigger than the equilibrium constant. So for 10 to go back to 5, I'm going to have to wind up making that ratio smaller, so the denominator has to get bigger. So the reverse reaction is going to wind up being spontaneous. So if the reverse reaction is spontaneous, the amount of AB molecules is going to increase maybe by 11, and the amount of A and B molecules will decrease, and it's a 1-to-1-to-1 ratio, so they would each decrease by 11. So now, when the reaction is shifted to the left for a while, eventually the forward and reverse reactions rates will be equal, and the ratio will equal the equilibrium constant one more time. Now, that's a lot of calculation to do here. There's actually an easier way to view this anytime you change the volume of a container. And that is, anytime you decrease the volume of the container, you're compressing the gas molecules. They're too close together. The spontaneous reaction will always be the reaction that creates the lesser number of gas molecules. And in our reaction at the top, we have an AB molecule as a reactant, and we have an A molecule and a B molecule as products. There's one gaseous reactant molecule, but there's 2 gaseous product molecules. So if we make the container smaller, the reverse reaction will predominate because it's causing 2 molecules to convert into 1. So a decrease in the volume, the reaction that produces the lesser number of gas molecules will always be the spontaneous reaction. Let's try that with this example right here. This is an equilibrium. It has gases in it. I'm going to ask you which way is it going to shift if the volume is decreased. So to do this, every time you do a change in volume, you have to look at the number of gas molecules on the reactant and product side. I've included some solids in here. You have to exclude those. They don't affect the volumes to gases. So on the reactant side, there's 1 mole of O2 gas, but on the product side, there's 2 moles of chlorine gas. So if you decrease the volume, you're compressing them. You've got to shift to create the lesser number of gas molecules, and 1 is less than 2, so the reaction is going to shift to the left so that the 2 moles of Cl2 get compressed into 1 mole of O2. So what happens to the moles of O2? They increase because the reaction's proceeding to the left. What happens to the concentration of O2? It's going to be higher now. Now let's see if we can do it the other way around. What if the volume is increased? Well, the exact opposite is true. If you make a volume bigger, you're going to have so much space in the container, you want to make the reaction shift to make more gas molecules to fill all that space. And so going to the right, you would cause 1 mole of gas to turn into 2 moles of gas. Shifting to the right, you would decrease the amount of O2 in terms of its moles and in terms of its concentration. Let's try one last reaction. This one is solid ammonium bisulfide decomposing into ammonia and hydrogen sulfide gases. And let's see if we can figure out the shift direction and then the moles of the H2S and the concentration of the H2S when we reach new equilibrium. If the volume decreases, the rule is you're going to shift to whichever side of the equation produces the lesser number of gas molecules. The left side has no gas molecules, the right side has 2. So it's going to have to shift to the left. Now, what's going to be true about the actual amount of H2S in the container? If you're shifting to the left, you're reacting it away. It's decreasing. But watch this. What's going to be true about the concentration of H2S? This reaction is a little bit special because if you write the equilibrium constant expression for it, what's missing from it? It doesn't have a denominator. It doesn't have a denominator. Watch what happens numerically here. For this reaction at equilibrium, let's say we have 20 molar of NH3 and 20 molar of H2S. What's our equilibrium constant? 20 times 20, it's 400. Okay? If we decrease the volume, what happens to those molarities? Containers smaller, they're going to be more compacted, they're going to be more concentrated. So if we change the volume from 1 liter down to 0.5, I'm just doing this because it's easy to calculate, the molarities would now be 20 moles per 0.5 liters, or 40, 20 moles per 0.5 liters, or 40 again. So we now have a situation that's not at equilibrium because 40 times 40 equals 1600. It doesn't equal the equilibrium constant. So the reaction's going to go to the left, the NH3 and the H2S are going to react away. And you got to figure out how far they react away. They'll go down to 39 and 39, 38 and 38, 37 and 37, 36 and 36. How far do they have to go down until they reach equilibrium again? Well, the equilibrium constant is 400. They're going to have to go all the way back down to 20 and 20 again. So you react away a lot of the H2S gas molecules so that now that you only have a half a liter container, their concentrations will once again be 20 moles per liter. So the answer is there'd be no change in the molarity of the H2S. In a big container, you have to have lots of moles of H2S to make a certain molarity. In a smaller container, you would have a lesser number of moles to make that same molarity, but the molarity doesn't change. If the volume were to increase, you would shift to whichever side creates the most gas molecules. And in this case, that would be the right side because 2 gas molecules is greater than 0. If you shift to the right, you'll be creating more H2S molecules for sure, but the opposite phenomenon is going to happen here. If you're starting with 20 and 20 as your molarities and you make the volume bigger, the molarities will go down to 10 and 10. As the reaction shifts to the right, they'll go up to 11 and 11, 12 and 12, 13 and 13. They're going to keep going up until they're 20 and 20 again. So they would actually have no change.